Today's video is about the artifact creation process from virtual design to manufacturing a tangible object. Nowadays, inexpensive 3D printers can be found in schools or even homes, making the creation of small to mid-sized artifacts relatively easy and less time-consuming than before. Inexpensive 3D printers typically refer to FDM models, which use PLA filament. Fused deposition modeling, FDM, is a manufacturing process that builds artifacts layer by layer using thermoplastic filaments such as polylactic acid, PLA. Later in the video, there will be a more technical explanation of FDM 3D printers. For virtual design of artifacts, a web-based tool like TinkerCad is an easy choice, available at tinkercad.com. Next, a time-lapse GIF will show the virtual design of a specific platonic solid, a tetrahedron, created as a wireframe in TinkerCad, followed by its manufacturing on an FDM 3D printer. The process will be broken down into quick session stages until the finished artifact is complete. Afterward, the full TinkerCad design session will be shown, detailing the step-by-step creation of the tetrahedron as a wireframe. As promised, the video concludes with a more detailed explanation of FDM printing.
it's a perfect solid in mathematical terms, I am going to use code blocks to create this. So after logging in, okay, I'm gonna create code block. I'm going to have a precise control on the dimensions of the solid, so it's going to be precise. It's a tetrahedron which has 4 sides in the shape of 4 equilateral triangles. So the first thing to do is this platonic solid, the tetrahedron, is going to be designed as a wireframe. Being a wireframe, it means that the sides of the 4 equilateral triangles that the tetrahedron is composed, those triangles are going to have sides. Okay, so those sides we're going to name linear units. Now in TinkerCAD, because we're going to use the object oriented paradigm, we first have to use so we have to create a template for linear unit, which is going to be 3 of those linear units are going to shape an equilateral triangle. So the first thing to do is to create a template. Okay, and the template is going to have as a name linear underline unit. Okay, so this is how to do it in code blocks. When you create a new template, there is the definition of it right here and the execution of the definition. So if this doesn't appear in this program area, the definition is going to do nothing. So to define a linear unit, first we have to define a cylinder. Okay, so let's go to the cylinder block. That's the one. Okay, so this cylinder, we're going to expand the parameters of that cylinder. Okay, the color we don't mind, it's going to be like orange like. Now about the dimensions. The work plane dimensions are 200 by 200 millimeters. So the linear unit has to be around 140 millimeters. So let's say 140 millimeters, and the radius, which is half of the diameter of the cylinder, it's going to be 6. So the diameter obviously is going to be 12. So if we, let's run it first, okay. Okay, we have to rotate this on the Y, which is, this is the Y axis. The axis is this green here. This is the Y axis. So if we rotate this, so we go to the modification, the modify menu, okay, and we take this rotate. Okay, we have to rotate it around the Y axis by obviously by 90 degrees. Okay, so let's zoom out and run this once more. Let's do it. Correct. So what we do is we have to move the Z axis of this shape, this cylinder, okay, to a minimum of 0. So let's do it, and this is how it's done. Okay, so you've seen it, all right. Okay, and we're gonna change the color. Obviously we're gonna have the same color, okay, and the parameter, the only parameter of a sphere is obviously the radius, and it's gonna have the same radius as the cylinder, which is says 6 millimeters. Okay, and obviously we have to raise it. So let's go to the modify menu and say Z-axis minimum to 0. But now we have to move the sphere, and this time for the X-axis, the center of it, okay, but this is going to be -50. So let's test it once more. One goes to this and the other goes there. Okay, so this is actually one side. What we can do now is let's group the cylinder and the spheres at both ends of the cylinder. Select all first, okay, and then do a group selection. Okay, and you will see that when grouping the selection, the boundaries between the solids, the solid shapes, are going to disappear, and this is going to be a unified piece. So let's do it. Yes, and yes, and look. So this now concludes the linear unit. So we actually built a linear unit, okay? So whenever we want to use one such unit, we just call it with this block command, create from template linear unit, and it will create this. So let's put that aside, okay, because it's finished, and make another shape. Let's make a template for an equilateral triangle. So create a template, okay, and give it a name like equilateral, Okay, so that creates a definition and a command. The previous command of the linear unit, we should enter it here. Now, to create a triangle, we just need to create 3 linear units. So, rotate it. Let's rotate. So, let's do it and put here 60 degrees. Okay. So, let's do this. Okay. Yeah, correct. Let's move along the y-axis first. Okay. Let's think of that if the diameter is 12, so we need -6, because -6 it has, remember here is a sphere that has a radius of 6 millimeters and a diameter of 12. That's the whole thing here. So we need 6 to be under this line and 6 to be over this line. So actually this needs to be the minimum, that is that one, is touching it has to be -6. Okay, let's do it and test it. Okay, watch. It is turning. Yeah, and see if this is what exactly this is what we need. Yeah, look at that. The sphere, remember, visualize here that this end is actually a sphere. Okay, so when we're going to create another linear unit, the 2 spheres at the end are going to contain one the other one. Okay, touching inside one another. That one to be touching exactly at the center of the y-axis, which is 0 on the x-axis. So this is going to be, the middle of it is going to be 0, the middle of the sphere. But because this is a compound object, we need, and here is the minimum and here is the maximum, so we need the maximum to be at +6. Okay, exactly the middle of the diameter. So we need to move the x-axis to 6 millimeters. So let's do it again. Okay, turn. Exactly. Now let's create another linear unit. Okay, so let's go to the templates, get another linear unit. To make it bigger, let's make it full screen. Okay, play. Right, so this is the first linear unit. It goes there, and now it's the second linear unit. Okay, so they're touching this side exactly where they should be. So let's see. Okay, make it smaller. Okay, so we have to select all. Remember, we need to do a compound of those two to a one compound. So select all, selection. Okay, then rotate around the z-axis. So it's rotate around z-axis. Okay, let's see it. So let's move it along the y-axis. Okay, and we need the minimum to be -6. Okay, make it faster. You see, a single play, a fast play. So we move it along the x-axis. Okay, and we need center and we need 0. So let's do it fast again. To complete the triangle, obviously we only need to have a linear unit along here. Okay, so go to the templates and get a linear unit template here. Okay, and when it finishes, we're going to select all. Okay, and group selection. So in the end, it's going to be an equilateral triangle, a solid wireframe. Okay, so let's do it fast. Okay, so now we have to do is create 3 more triangles, and then our tetrahedron is going to be ready. So our triangle is ready. So what we do is keep this right, and now we have to create another template, which is our final solid shape tetrahedron. Okay, so we need a tetrahedron template. So we go to the template here, create a template and name it tetrahedron. Okay, here it is, the definition and the actual block command. So to create a tetrahedron, we first have to create an equilateral triangle, raise it, let's do it, okay, rotate around the x-axis for sure, and we have to use, so 109.5, I think. Let's test it. Okay, move the z-axis to 0 as we did it. Okay, so let's do it. Okay, so rotate z-axis by 60 degrees. Okay, let's do it fast. Okay, so move x-axis maximum to 6. Which is this side here. Okay, so remember we need this shoulder to be in the middle of this line. So if this is 12, the diameter 6 is going to be half of it. So yes. Alright, and move the y-axis minimum to -6. Okay, fast. Okay, so it's going to be raised. We need another equilateral now, so I have to go there. Okay, take it from here. Okay, and fast, play fast. So it's one triangle, another triangle. Okay, so we have to raise this again. So move along the z-axis, the minimum to 0. Okay, so move y-axis, minimum to -6. Last we need the last triangle. Okay, and we are ready. So we go to the template. Okay, get another equilateral triangle. Okay, and see what we have. Okay, let's view it from this angle. Okay, and see how it's going. Yep, and our tetrahedron is finished. We just need to move it to the center of the plane, which is 0, 0. Okay, so the last command is to select all of it. Okay, group all of it, group the selection, and move it along, because the x-axis is centered, move it along the y-axis. So move y-axis to center is 0. Okay, let's do it and it fast. And we waited. Okay, look at that. So now it is ready. Okay, so this is the actual program, the code block for the whole tetrahedron. See that? We take the STL, feed it to a 3D printer, and manufacture the actual artifact. Change the name from Glorious Go-Go to Tetrahedron Wireframe. So now we go to Share STL and we'll wait for it to be. Yep, the wireframe is ready. And what you know, that if when using a 3D printer, Okay, load the STL we just downloaded from TinkerCAD. Right, go here, import, and that's the one, tetrahedron, and that's the one here, slice plate. And it is ready to be printed. Thank you for watching.
FDM 3D printing with PLA filament, a more detailed explanation. The 3D printer's motion system moves the nozzle and bed in 3D space. Stepper motors move in discrete steps with torque and acceleration limits. Sudden changes in direction can cause vibrations, so special printer firmware detects the acceleration and jerk limits to smooth out nozzle motion and avoid ringing or ghosting. Gaps in mechanical components, for example belts, lead screws, etc., can cause inaccuracies, so high-quality printers minimize this with preloaded components. That is, the mechanical components are placed under tension or compression before they are used in operation. PLA absorbs moisture, which can cause bubbles or poor layer adhesion. Drying the filament before printing is often necessary. PLA filament is pulled from the spool and pushed through the nozzle by the extruder motor. The extruder must grip the filament firmly to avoid slipping. The extrude gear applies a force at right angles to the filament, creating friction. The filament should be compressed slightly by the extruder gear because too much pressure can deform the filament. This higher pressure at the inlet from the extruder forces the PLA to flow more easily during extrusion out of the nozzle exit. PLA is a semi-crystalline thermoplastic that softens and melts when heated. Below 60 degrees Celsius, PLA is rigid. Above it, it becomes soft and rubbery. Above 180 degrees Celsius, PLA becomes fully molten and flowable. The printer's nozzle heats the filament to the aforementioned temperatures using a resistive heater. The heat must be conducted uniformly to avoid cold spots or overheating. As the temperature increases progressively, so is the flow of the molten PLA filament through the nozzle. At the right temperature, the molten PLA filament's flow properly holds its shape after deposition, but it is fluid enough to extrude smoothly. Once extruded, the molten PLA must bond to the previous layer or the build plate. PLA adheres well to itself when hot due to polymer chain diffusion, PCD. The core mechanism of PCD occurs because the molten PLA consists of long polymer chains that slowly interdiffuse with the cooler, almost solidified material from the previous layer. This process is driven by the thermal energy retained in the molten material and the mobility of the polymer chains at elevated temperatures. In other words, when two adjacent layers are deposited, their surfaces must merge to form a strong bond. Molten PLA has surface tension, which helps it wet the previous layer. Higher temperatures increase material flow, improving wetting. The polymer chain's interdiffusion is time dependent and requires the layers to be hot enough for long enough. PLA's thermal contraction, that is, PLA shrinks slightly as it cools, can lead to warping if not managed, especially in thin parts. Cooling fans can cause uneven cooling, leading also to warping or poor layer bonding, so usage of the following is recommended. Heated build plates for better adhesion. 3D printer enclosures to maintain uniform temperature. Rafts, which are multi-layered platforms printed underneath 3D models and sometimes around them. Brims, which are thin, flat layers of material printed around the bases of 3D models, but not underneath them. Let's hope that by understanding and taking into account all aforementioned information, 3D printed models with PLA filaments are manufactured with better quality, strength and reliability. Thanks for watching.